conductance on different factors. So one of the factor is temperature. So there I have mentioned that conductance, if it is equivalent conductance and molar conductance, it increases with increasing temperature because of increasing ionization. And for specific conductance also, which is only for 1 unit volume, that is the number of ions present in 1 unit volume. For specific conductance also, the relationship with temperature, it is also directly proportional. So for all the conductances, it is directly proportional to temperature. But if you are considering dilution, then the relationship with dilution, that is not same. That is for specific conductance, that is relationship with dilution is decreases with dilution, but equivalent conductance and molar conductance increases with increasing dilution because of increasing ionization. But when it is temperature, all the three types of conductances all are increasing with increasing temperature. Fine. Here we have a problem. A 5 millimole. Be very careful about the units. It is millimole, not mole. 5 millimole per decimeter cube aqueous solution of KCl, which is strong electrolyte, and conductance mentioned 0.55 millisiemens. ms, that means millisiemens. And when it is measured in a cell constant, 1.3 centimeter inverse. So here simple conductance is given. It is not equivalent, it is not specific, and it is not molar also. Okay. So we have to find out the molar conductivity of this solution in millisiemens meter square per mole unit. Okay. So we have to be very careful about the units. So first of all, what we will do, the concentration that is given is 5 millimole per decimeter cube. Okay. So as that is finally the unit should be millisiemens meter square per mole. So first we will convert it to mole. So for that we have to multiply with 10 to the power minus 3, because we are moving from millimole to mole. And also from decimeter we have to move to, first we will move to centimeter. Okay. Then from centimeter we will move to meter. So if we convert decimeter to meter, as it is per decimeter, that means when it will be per centimeter, it will be lesser. Okay. So this is the number of moles. Right now I will write in 1 liter. That means in 1000 ml or cc. Okay. So we can write that 5 into 10 to the power minus 3 number of moles that is present in 1000 cc or ml. So 1 mole will be present in 1000 divided by 5 into 10 to the power minus 3. So this will be 10 to the power 6 by 5 centimeter cube. Okay. So this is actually the molar volume. This is molar volume, that is Vm. Okay. Because to calculate specific conductance, we require the molar volume. And next what we will find out, we know that kappa is equal to conductance C divided by multiplied by L by A. This is cell constant, so I am writing it as conductance multiplied by cell constant. So conductance value is given 0.55 millisiemens. We will not convert millisiemens to siemens, because ultimately we have to convert it to millisiemens. So it is 0.55 millisiemens and cell constant is 1.3 centimeter inverse. So here also we have centimeter, here also we have centimeter. So same unit must be present. So 0.55 multiplied by 1.3, it is 0.715 millisiemens per centimeter. Okay, so now we know what is kappa, we know what is molar volume, so we can easily find out what is the molar conductivity, because molar conductivity M, that is equal to kappa into molar volume. So kappa is 0.715 millisiemens centimeter inverse, and molar volume is 10 to the power 6 divided by 5 centimeter cube. So it will be 0.143 multiplied by 10 to the power 6 millisiemens centimeter inverse centimeter cube. So ultimately it will be centimeter square. Okay, and basically if it is molar volume, then it is actually centimeter cube per mole, that is 1 mole having volume centimeter cube, so centimeter cube per mole. So you can write here per mole. So ultimately it will be having unit ms, millisiemens centimeter square per mole. Now it is in centimeter square, but we have to convert it to meter square. So that is why we will multiply it with 10 to the power minus 4, because when we are moving from centimeter to meter, it is actually, it should be multiplied by 10 to the power minus 2, but as there is centimeter square, so it will be 10 to the power minus 2 its square, that means 10 to the power minus 4. Now the unit is ms, meter square per mole. So this is the unit in which we have to express it. So 0.143 10 to the power 6 10 to the power minus 4, that means 10 to the power 2. So ultimately it will be 14.3 millisiemens meter square per mole, and if it is rounded off to nearest integer, it will be simply 14. So the answer will be 14. Okay, next question. This is simple question. Amongst the following, the form of water with the lowest ionic conductance at 298 Kelvin. So here we have different types of water: distilled water, water from a well, saline water used for intravenous injection, and seawater. Now we know that ionic conductance, obviously that will increase, that will be directly proportional to number of ions. So if number of ions are high, this will also be high. If it is low, then the value of ionic conductance, that will also be low. When it is distilled water, it is actually free from most of the ions, because in natural water there is presence of some ions always. It is not that there is water is always pure. So in normal water there is always presence of some ions, but if we distill the water, then it is free from ions. That means ion number is almost nil or very minimum. That means it should have lowest ionic conductance, because for all other three options, that is water from well, that is a natural form of water, or saline water used for intravenous ingestion. Saline water means what? There will be presence of sodium chloride, and also seawater where also presence of sodium chloride. So sodium chloride, it is strong electrolyte, so number of ions of Na plus Cl minus, it will be very high. So that is why your correct option will be distilled water, because we have to find that water which is having minimum ionic conductance, and minimum ionic conductance, it will be for distilled water. So correct option is distilled water. Now we will see how the conductance, it is changing with concentration or dilution. We have already seen that what are the factors on which conductance is dependent. Some of the factors we have seen, that is temperature, ionic mobility, nature of solute, whether it is strong or weak. So depending on all these, how it is changing, that is different types of conductances, specific, molar and equivalent, that we have already seen. But now we will see the most important factor on which conductance is dependent, and that is on concentration or dilution. Now you can say that how conductance is changing with concentration, and you can also explain it in terms of how conductance is changing with dilution. So when concentration is very high, that means it is not dilute solution, it is very concentrated solution. And when concentration is low, then the solution is dilute. That means concentration and dilution, these two are inversely related to each other. As you are increasing concentration, basically it is becoming less and less dilute. Okay. The specific conductance, that is kappa. So specific conductance means the conductance produced by all the ions which is present in unit volume. Fine. So it will decrease with decrease in concentration. That means with increase in dilution, because it is opposite, both for weak and strong electrolyte. So it doesn't matter whether you have weak electrolyte or strong electrolyte, it will always decrease when concentration is decreased, because as the volume is specific, here volume is constant, that is unit volume. So when it is unit volume and you are decreasing the concentration, that means number of ions will decrease, and if number of ions decrease, obviously kappa will also decrease. And the reason is written here, this is because number of ions per unit volume that carry the current in a solution decrease on dilution. So this is the reason. But what about the other two types of conductances, that is molar conductance and equivalent conductance. Now both molar conductance and equivalent conductance, that is lambda m and lambda e, increases with increase in concentration. Okay. Now why it is so? So here as increase with decrease in concentration, that means now the solution is very dilute. So here total volume V of the solution, okay, this is the molar, sorry, it will be M, that is molar volume, and this you can write as N. That means the volume in which one equivalent of the electrolyte is dissolved, that volume is Vn, and Vm is the volume of the electrolyte solution where 1 mole of the electrolyte is present. So this is because total volume of the solution that contains 1 mole of electrolyte or 1 equivalent of electrolyte in case of equivalent conductance, that also increases, because here volume is not fixed, unlike kappa which is specific conductance where volume is fixed. Here volume is not fixed. Here the concentration, that is 1 mole and 1 equivalent, that amount is fixed. But when you are decreasing the concentration, that means now volume is very high, but according to the definition of lambda m and lambda e, it is, they are the conductances produced by the ions which is coming from 1 mole of the electrolyte or 1 equivalent of the electrolyte. Okay. So as with dilution, dissociation of electrolyte increases, especially for weak electrolyte. So that is why both of these value increases. Okay, because here volume is not fixed, volume will also increase. But one thing is also there, that lambda e and lambda m, that is also directly proportional to kappa, but with decrease in concentration, kappa is decreasing. So Vm or Vn, these two are increasing, that is why lambda e, lambda m increasing. But what about kappa? Because kappa is decreasing, so according to that lambda e and lambda m should also decrease, that is two factors are opposing to each other. But it has been found that decrease in conductivity on dilution of a solution, that is more than compensated by the increase in its volume. So here decrease in the value of kappa with decrease in concentration, that is overcome by the increase in Vm or Vn. Okay, so that is why ultimately the value of lambda m and lambda e, these two will increase with decrease in concentration. So it is inversely proportional to concentration. So here we have a graph, that is strong electrolyte and weak electrolyte, how the conductance, it may be equivalent conductance or molar conductance. So this lambda, it may be lambda m or lambda e, but not kappa. Okay, so for strong electrolyte, how it is related to root C. So root C means it is root of concentration. So when you are increasing the value of concentration, as we are moving from left hand to right hand side, C value is increasing. And see, when concentration, suppose I have chosen 2 points. This is one concentration, this is another concentration. Now concentration 1, 2. Concentration 1 is lower than 2. Okay. Now when at point, we are at point 1, if we draw a line on this, here the corresponding value of conductance is somewhere here. But if you draw a line from 2, that is high concentration, now the corresponding conductance that is at this point, that means conductance is low. So here slope is basically negative. That means inversely related to each other, the factor which is in y-axis and another factor which is at x-axis. Okay, and for strong electrolyte, here you can see, as we are diluting the solution, that is as we are moving towards lesser C value, that is suppose at point 1, gradually, that is this increase in the value of conductance for strong electrolyte, it is very slow increase. It is not very drastically increasing. Okay, it is very slow and gradual. But now if you look at weak electrolyte, when we are at concentration 2, that is very highly concentrated, now the corresponding lambda value, it is even lower than the strong electrolyte, because at point 2 for strong it is somewhere here. Okay, now when you are moving to very low concentration 1, the corresponding lambda value for strong electrolyte is here, but if you draw a line for weak, this is almost here. So basically I mean to say, here the increase of strong electrolyte with dilution, that is lambda is increasing in a very slow manner, but in case of weak electrolyte, there is a sudden increase in the value of lambda as we are moving towards more dilute solution. So this side is dilute solution and this side is concentrated solution. Okay, so remember the nature of change of lambda with dilution, it is of different kind in case of strong electrolyte and in case of weak electrolyte. Fine. Why it is so? Because for weak electrolyte, here the ionization drastically increases as we are decreasing the concentration, but for strong electrolyte that is not the case. We know that for strong electrolyte it is always almost dissociated, 90% or 100% dissociated, but if it is weak electrolyte, maybe the dissociation is 40% or 20% or 50%. It is never too close to 100%. So that is why with dilution the effect of increase, in both cases it is increasing, but the nature of increase is not similar kind. Okay, and here this equation, as this is the intercept on y-axis, so as if here when it is touching this y-axis, the corresponding value of concentration is basically 0. So at 0 concentration, the lambda value that we are getting, that is known as infinite, that is conductivity at infinite dilution. So this point as concentration is 0, that is root C will be 0, that means it is infinite dilution. So when it is infinite dilution, the conductance, that is maximum value. So this maximum value is denoted by lambda naught, or sometimes you can see that it is also expressed like this. So it means that it is the maximum conductance that is possible, which is at infinite dilution. But by extrapolating this line, that is touching this line on the y-axis in case of strong electrolyte, you can easily find out what is the value of conductance at infinite dilution. But if it is for weak electrolyte, you can see that this line is never touching the axis, right? So what to do for weak electrolyte, how we should get lambda infinity value? So there is another solution for that, we will come into it. But before that, what will be the equation for this type of graph? It is actually lambda lambda 0 minus some constant into root c. So this constant is basically slope. This is in x-axis, slope is m. This is intercept I, and this value is y. So you can compare this equation with y equal to c plus mx, where c is intercept. Okay, c is intercept, y is lambda, m is slope which is minus k, and x is root c. Okay, so why it is important to understand the nature of graph? Because you can get question which are related to graph also. That is, some graphs will be given in options maybe, and you have to find what is the correct nature of the graph, and that is why you should know that this is the equation for straight line which is not going through origin, because here we have intercept and slope is negative. Now another graph we have here. This is lambda m, or also you can say lambda e. Now when it is we have the plot of lambda versus concentration, what will be the effect that we have seen in the previous graph. But in this case it is dilution, and we know that with dilution it will directly increase. As you are higher is the dilution, higher will be the value of lambda m or lambda e. So that is why here the nature of the graph is, see, it is increasing with dilution. So be very careful whether in x-axis concentration is mentioned or dilution is mentioned, because mostly you will see that concentration will be mentioned. So if it is so, it is very easy to understand from this graph, but be careful, because if it is with respect to dilution, now the nature of the graph, it will be opposite. Okay, because with dilution it is directly proportional. So when you are increasing dilution, suppose you are somewhere here, corresponding value of lambda is here, but when you are having very dilute solution, the point is here. Now the corresponding line, if you draw on the y-axis, see, now lambda is also increased. Okay, so this is directly proportional to dilution. But if it is concentration in the x-axis, that is root c, then it will be opposite relationship. Okay, now we will focus on this graph, that is what are the significance that we will find out, especially the infinite dilution. So strong electrolytes like KCl, we know that high value of conductance even at low concentration. But if it is weak electrolyte, that is not the case. So that is why strong electrolytes, there is no rapid increase in their equivalent conductance. It is gradual increase. Okay. Now for strong electrolyte, there is a tendency for equivalent conductance or molar conductance, because here lambda m is written, it can also be lambda e, to approach a limiting value. Limiting value means when you are touching this line, that is, you are extending this line, it will touch the y-axis at some point. Okay, and that point is a limiting value when the concentration approaches 0, because at this point C is 0. When whole of the electrolyte has ionized, that is 100% dissociation. So further addition of water does not bring any change in the value of equivalent conductance, because you have already reached the minimum value of concentration. So whether you further add water, it doesn't matter. So remember, this stage is infinite dilution. So this I have already said in the previous slide, and this equivalent conductance or molar conductance, it will now have a limiting value which is expressed by this, and sometimes it is also written like this. Okay, lambda naught. Now what about weak electrolyte? In case of weak electrolyte, for example, suppose you have acetic acid. Now when it is very high concentration, the electrolyte, it will have very low value of conductance, and there is a low value of conductance of lambda. Okay, and there is a rapid increase in the value of conductance with dilution. So this is the rapid increase, suddenly it is rising. There is no indication that a limiting value of equivalent conductance or molar conductance can be attained. So it is never touching the y-axis. Okay, so that is why when the concentration is approaching 0, we are not able to get the value of lambda infinity. So graphically, lambda infinity for weak electrolytes we cannot get, but there is a solution, and the solution is Kohlrausch law. Okay, so how to apply this law, that we will see, but before that we have to understand some experimental observation. So what are those observations? Here we have a table. This observation is related to at infinite dilution. Okay, so before starting Kohlrausch law, so first of all we have to understand this experimental observation. So here we have some molar conductivity values at infinite dilution of some strong electrolyte, and what is the important thing is here is they are having common ions. Okay, so first look at the left hand side column. Here we have NaCl KCl, so this is a pair, then NaNO3 KNO3, then NaOH KOH. So what is common here? In each case the anion is common, right? And the metal is sodium potassium. Then again anion is common, but sodium potassium. Anion is common, but metal again sodium and potassium. Now look at the corresponding lambda m infinite value. This is these are the values. Values are not important. Important is what is their difference. So difference is 23.41. In case of the second pair also it is 23.41. Here also, that is in the last pair also it is same. So from this observation, what is the significance of this observation? The significance is here what is the nature of anion, because it is common, it has no effect, because when you are changing the anion from Cl to NO3 to HO minus, basically there is no effect on this difference value. That means Na plus and K plus, if we take the difference, it is, if you are fixing the metal it will always be same. That means there is no effect of the counter ion. Okay, the contribution of the conductance for these cations, they are independent of the nature of anion. Similarly, now in the right hand side again we have a column of electrolyte, but now what we have done, we have fixed the metal. Now anion is changing. So when anion is changing, see it is Cl and Br, then again ClBr, ClBr. But what is common thing here? Sodium is common, then potassium is common, and in the last case ammonium ion is common. Fine. Now see here also the difference is same value. That means whatever is the nature of cation, in the first pair it is Na plus, then K plus, then ammonium plus. It doesn't matter on the value, that is difference between the value of Cl and Br. So basically as if here the value of sodium, that is a contribution of sodium, it is decreased because you are taking the difference, that is 128.51 minus 126.45. So when we are taking the difference, the value of Na plus, that is the value of individually the value of the cation, as it is same, it is cancelled out. So that is why each time the difference is same. So as if you are taking the difference of Br and Cl in each time, because as cation is common, it is cancelled each time when you are deducting the value, that is 151 minus 149 or 151 minus 149 in this way. Okay, so this is the experimental observation. Now we will elaborate it. See here KCl and NaCl, we are focusing on these two. Here anion is common, these are the values, that is just like these two. Difference is 23.4. So how we are getting is, this is lambda naught of KCl, that is infinite dilution. This is lambda naught of NaCl. Now we have just break it in two parts. Now it is lambda naught of K plus, lambda naught of Cl minus. That is independent contribution of K plus and Cl minus, cation and anion. Then minus lambda naught of Na plus, lambda naught of Cl minus. So as the value of lambda naught Cl minus, it will be same. So that is why these two as if cancelled out. So ultimately it is a difference of lambda naught K plus minus lambda naught Na plus. Similarly, if you consider these two, here also anion is common, which is iodide. So in the second table, similarly, that is just follow the same thing, lambda naught of cation, then anion, lambda naught of cation, then anion. As anion is same, these two are having same value. That means at infinite dilution, this value, which is for potassium plus, it is fixed. It is not dependent on the nature of anion with which it is associated. So here potassium is associated with Cl. Here potassium is associated with I minus. But that doesn't matter because you are now at infinite dilution. So the contribution of K plus, that is independent of the nature of its counter ion. Okay. So this experiment, from this experimental observation, we can derive the Kohlrausch law. And this law has some important applications. So this is actually an indirect method for obtaining lambda infinite value for weak electrolyte, because from the graph we have seen that by in extending the straight line, it is not crossing the y-axis. So we are never able to reach that is to get the value of lambda infinite for weak electrolyte. So that is why what we can do, indirectly we can find out the value of lambda infinite for weak electrolyte, because for strong electrolyte it is very easily we can get it from graph, but graphically we cannot get it for weak electrolyte. So what it says, at infinite dilution when dissociation is complete, okay, because it is always considered that when concentration is minimum, then it is at infinite dilution, and dissociation of weak electrolyte, it is 100%. So each ion will make a definite contribution towards the molar or equivalent conductance. That means each ion means cation and also anion, irrespective of the nature of the ion with which it is associated. That we have already seen from the experimental observation. And the value of conductance, whether it is molar or equivalent, whatever, at infinite dilution for any electrolyte, it is always the sum of contribution of its constituent ions, that is anions and cations. And it is true not just for weak electrolyte, it is also true for strong electrolyte. Because though in case of strong electrolyte, from graph directly you can measure the lambda infinite value, but the law is applicable for both the electrolyte. Okay. Now how to find it out? Here for HCl, if it is a molar conductance at infinite dilution, if you know the value of lambda infinite of H plus ion and Cl minus, directly you can add these two and you can directly get the value of lambda m. You don't need the graph. Fine. Now you can say that for strong electrolyte like this, we can easily get it from graph. Yes, that is fine, but it is also true for the strong electrolyte. But basically these are important for strong electrolyte, for weak electrolyte. For example, acetic acid. Here from the graph we cannot get it. But if you know the value of H plus and acetate ion individually, then you can add these two and you can get the value of lambda m infinite. And here one thing you have to notice, here it is molar conductance. Fine, lambda m, 1 cation, 2 anion. So that is why it is 2 into lambda infinite Cl minus. Similarly for Al2SO4 3, it is 2 cation, so 2, that is the coefficient is 2, and here it is 3 because we have total 3 sulfate. So in this way we can calculate. But suppose if it is this type of electrolyte, that is AXBX, so obviously it will dissociate as XAY plus, that is the charge, the number y here, that is actually the charge of A. Okay, so you can take the example of Al2SO4 whole 3. So here X is 2, Y is 3. Fine. So when Y is 3, basically aluminium, its oxidation state is +3, and as this is the number of aluminiums, then the oxidation, that is overall charge of sulfate ion, that is also -2. So the anion, total number of anions, that will be having the same value. So that is why it is written as XA Y plus YB X minus. Okay. Now if it is equivalent conductance, how you will express it? It is expressed in this way. What you are doing? You have taken the value of lambda, sorry, it will be A, it is B. Okay. So for A, this is the charge, right? So this is actually Z and this is Z minus. Okay. So we will write the equation in this way because right now you are calculating lambda equivalent. So when it is molar conductance, you will follow this type of you have to do the calculation in this way. You are multiplying the number of cations and anions directly with the value, but now what you are doing, you are dividing it by the charge that is present, and it has nothing to do with how many A plus or A plus Y or B minus X is present. This number is not important, but you have to divide it by the charge. Okay. If it is plus 1 charge or minus 1 charge, then it will not matter. And minus charge, that doesn't mean it is Z minus value. Z minus, it is written here, but if it is minus charge, don't think that you have to put minus 1. You have to take only the numerical value, which is 1. So now we will see how we can do it. So lambda infinite BaCl2, if we calculate, that is, now we are calculating lambda equivalent. So what we have done, as the charge of barium is 2 plus, so it is 1 divided by 2, and charge of Cl minus, it is 1, so it is 1 by 1. So though there are 2 chloride, but that we have not considered. Then aluminium chloride, aluminium is plus 3 charge, chloride has minus 1 charge, so it is 1 by 3, 1 by 1. Then Al2SO4, 1 by 3, because charge of aluminium 3, charge of sulfate is minus 2 for each sulfate and so that is why it is 1 by 2. So in this way we can calculate lambda M and lambda E. Applications of Kohlrausch law. So there are very important applications of this law. Total 4 applications we will see. First of all, calculation of molar conductivity at infinite dilution for weak electrolyte, because graphically we cannot determine what is the molar conductance at infinite dilution, which is possible for strong electrolyte but not for weak electrolyte. Then calculation of dissociation constant for weak electrolyte, calculation of degree of dissociation of weak electrolyte, and calculation of solubility of sparingly soluble salts. Sparingly soluble means the salts which are having very poor solubility. So we can also calculate the solubility, and if you can calculate the solubility, obviously you can also calculate KSP, that is solubility product. Okay. So first we will see how we can calculate the molar conductance or conductivity at infinite dilution for weak electrolyte. The first application, calculation of molar conductivity at infinite dilution for weak electrolyte. So here we will calculate molar conductance of acetic acid. Okay. Now here some informations are given. So what are the information? The first information is lambda naught value, that is molar conductance at infinite dilution for HCl. The value is given, and see, HCl is strong electrolyte. So obviously you can easily get the value from that is graphically you can easily get it. Then we have the value of molar conductance of NaCl, which also you can get graphically, and sodium acetate. Now this is a salt of acetic acid, but ultimately it is a salt and its dissociation is also complete, so this is also strong electrolyte. So that is why value can be easily available. Now by taking the help of these 3 values, we can calculate the value of molar conductance at infinite dilution for this weak electrolyte, which is acetic acid. So how we are doing this? First write the value of HCl and add it with sodium acetate. Okay, so here our purpose is basically to cancel out the value of Na and Cl, and how we can do so? By subtracting lambda naught M of NaCl, because we just need H plus and acetate, and as they are having independent contribution, that is You can also write it as lambda m naught for H plus, then lambda m naught for Cl minus. So what will happen? The value for lambda naught of Cl minus, it will be cancelled because ultimately there is a negative sign, and lambda naught m of Na plus, that will also be cancelled. So what will be remaining? The remaining two factors will be lambda m of H plus and lambda m of acetate ion. Okay, so which is nothing but this one, that is lambda naught m. So in this way, by taking the help of infinite molar conductance for strong electrolytes, we have to arrange this in such a way so that ultimately we are having these two, this cation and anion, combination of which will give this weak electrolyte, that is H plus ion and acetate ion. Because this discussion is all about infinite dilution. If it is not infinite dilution, obviously you cannot do this. Okay, that is this type of subtraction addition we cannot do. It is possible only at infinite dilution, because at infinite dilution the counter ion, what is its nature, that is not important. All cations and anions are having independent contribution. Okay, this is the first application. Second application, calculation of degree of dissociation of weak electrolyte. So weak electrolyte, it is never completely dissociated. So molar conductivity at infinite dilution, it is maximum because dissociation is almost complete, near 100%. So suppose lambda mc is the molar conductivity of a solution at any concentration C, and lambda m infinite, that is the molar conductivity at infinite dilution. That means concentration is now 0. So degree of dissociation, this will be equal to number of dissociated ions divided by number of total ions present. So this is actually the theoretical, if you consider that all the ions are ionized. Okay, suppose if for simply try to understand, suppose there are total 5 molecules of HCl. Okay, HCl, and among these only 2 is dissociated at concentration C, but these 2 are undissociated. But when it is infinite dilution, then it will be acetic acid, not HCl. Okay, I am writing HOAC. Let me erase it. Suppose it is any weak electrolyte, in general I am writing any weak electrolyte HA. So 3 are undissociated, 2 dissociated, these 2 are dissociated. But at infinite dilution, all the 5 molecules of HA are dissociated. That means now you have total, for each molecule you are getting 2 ions. So now you will have 10 ions. Okay, and if only 2 are dissociated at concentration C, then your number of ions will be 4. So alpha will be now 4 divided by 10. Okay, so this is actually this ratio, number of dissociated ions by number of total ions present when it is infinite dilution. So that is why this ratio can be written as, this is equal to lambda m, that is molar conductance at a particular concentration, and divided by molar conductance at infinite dilution. Now this ratio, it will always be lesser than 1, it will be a fraction, because lambda mc, this is always lesser than lambda m infinite. Okay, that is why it will be fraction. And this value of lambda m for the weak electrolyte, that is value of basically lambda m infinite, that we can easily calculate using Kohlrausch law, that we have already seen in first application. Okay, that is in the previous slide we have already seen this lambda mc lesser than lambda m infinity. So we have already seen how lambda infinity m for weak electrolyte, that is this value, it can be calculated using Kohlrausch law. That is the first application that we have seen. So from the first application, first you can determine lambda in infinite, then if this value is known, then from this ratio we can get degree of dissociation, which is alpha. Third application, calculation of dissociation constant for a weak electrolyte. Now, if you know the degree of dissociation, that is, if alpha is known, then dissociation constant of the weak electrolyte at concentration C can be calculated. Now, how it is so? Suppose we have acetic acid, it is dissociated in acetate ion and H+. Initially, the concentration is C and these two will be 0, and after time t, degree of dissociation alpha. So, out of C moles, suppose C, that is C into alpha, that means some fraction of C is dissociated. So, the remaining undissociated form will be C minus C alpha. And when, as it is related to 1:1, that is, when you have taken 1 mole of acetic acid, you will get 1 mole acetate ion, 1 mole H+. So, when C alpha amount is dissociated, obviously the amount of acetate ion will also be C alpha, H+ will also be C alpha. Now, dissociation constant of this weak electrolyte, it is the concentration of anion and cation. That is, in the numerator, first you have to write the concentration on the product side divided by concentration on the reactant side. So, C alpha into C alpha divided by C minus C alpha. Now, we can take C common. Okay, C is cancelled. So, ultimately Ka is equal to C alpha square divided by 1 minus alpha. So, if you know the value of alpha and concentration, you can find out the value of Ka. Inversely, if you know the value of dissociation constant and C, you can also calculate alpha. Okay, and most of the time this alpha is very smaller than 1. So, 1 minus alpha, it is almost equal to 1, because with respect to 1, alpha is very small. So, whether you subtract it or whether you do not do it, that doesn't matter much. That is why it is almost equal to 1. So, ultimately it becomes C alpha square. Okay, so Ka is C alpha square. Fine. The last application, calculation of solubility of sparingly soluble salt. So, we have seen that NaCl, KCl, all these salts are considered as strong electrolyte. But there are some salts, suppose we have silver chloride, barium sulfate, lead sulfate, etc., which dissolve to a very small extent in water, very small. Okay, so that is why they are known as sparingly soluble. Now, as their solubility is very low, so even if you make a saturated solution, it doesn't matter, the concentration will be very low. So, it is so low that you can assume it as if it is at infinite dilution. Okay, and as their solutions are saturated and it is almost equivalent to infinite dilution, now you can consider concentration to be equal to solubility. Now, what is the difference between concentration and solubility? Solubility is the maximum concentration of any compound that is possible. Okay, that is when you have made saturated solution, under that condition the maximum concentration. But if you simply say concentration, it can be any concentration. But when you are saying, you are using the term solubility, that means maximum concentration that is possible. So, when it is saturated, that means it is all we have already reached the maximum solubility. So, under that condition, concentration will be equal to solubility. So, now if we use this equation that we have already seen, that molar conductance at infinite dilution. Now, this is infinite dilution. Okay, kappa 1000 by molarity. Okay, now this molarity is not just any molarity, it is molarity under that condition when it is saturated solution of sparingly soluble salt. Okay, so that is why this molarity now it can be replaced by solubility. Fine. So, if this value is known, kappa is known, we can find out the value of solubility and vice versa. And once you know the value of solubility, you can easily find out the value of Ksp. So, for example, suppose we have just take this salt BaSO4. So, when it will dissociate, it will be Ba2 plus sulfate 2 minus. So, suppose the solubility is, normally it is denoted by S. So, this will be S, this will also be S. So, Ksp is basically the concentration of barium 2 plus and sulfate 2 minus. So it is S into S, that is S square. So if you know the value of S, which is nothing but the solubility or molarity, then directly you can obtain Ksp value. And if you know the Ksp value, then also you can calculate solubility, and you can use this equation. Suppose any of these two is unknown, then using the other two known variable, you can calculate the unknown one. Fine. So regarding all these applications, now we will solve some problem, so your idea will be clear. So in this problem, basically what are the informations given? 3.06 10 to the power minus 6 ohm inverse centimeter inverse. Sorry, it is it's not fully mentioned. It is conductivity of a saturated solution of aluminium chloride type of salt. That value is 3.06. I missed it. Okay, 3.06, and from the unit also you can understand that this is conductivity. Conductivity means specific conductance, kappa. Kappa is given. This is kappa. While equivalent conductivity, that is lambda E of the same salt, that value is also given. Okay, ohm inverse is nothing but Siemens, S. It can also be written as mho unit. So there are basically three different units, all are actually same: ohm inverse, Siemens or mho, MHO. Ksp of this salt, four options are given, right? So we know that lambda m divided by lambda E, that is equal to Z, that is the relationship between molar conductivity and equivalent conductivity, is this, where Z is the total positive charge or negative charge. So this relation we have already seen. Here equivalent conductivity is given, but we require lambda m because we have to finally calculate Ksp, and for Ksp we need solubility, and for solubility we should know what is the molarity, and to know molarity we have to know lambda m, but lambda E is given, so that is why we are taking the help of this equation. Now what is Z value? LCl3. LCl3 is having Al3 plus cation, so Z value will be, and total negative charge is also minus 3, so Z value will be 3. Just take the numerical value. Lambda m is 3 into lambda E, which is 3 into 1.02, right? So 3.06 ohm inverse centimeter square per equivalent. So this is the value of lambda m. Now we will use lambda m equal to kappa 1000 divided by molar concentration in molarity. So I am writing m. Now m is unknown. Basically m we have to calculate. Kappa is known. Lambda m we have just calculated. So kappa is 3.06 ohm inverse centimeter inverse 1000 and 3.06. Unit you can write or not, that is up to you. So ultimately this will be cancelled, and ultimately what you will get, sorry, 10 to the power 6 that I missed here. Kappa is 3.06 10 to the power minus 6. So 10 to the power minus 6 and 10 to the power 3, ultimately it will be 10 to the power minus 3. It is per mole, not equivalent. because we are calculating molar conductivity, so it will not be per equivalent. Per equivalent unit is for lambda E. So it will be finally the molarity. Okay, so now we know the molarity. So when we know the molarity, we can easily find out what will be the Ksp value. AlCl3, Al3 plus 3Cl minus. So solubility, if it is S, then we will write S here, but for Cl minus it will be 3S, because per aluminium you are getting 3 chloride ion. Ksp will be S into 3S and also Q, because whatever will be the coefficient you have to put it in power. So if it is 2S, it will be 2S to the power 2. If it is 4S, it will be 4S to the power 4, like this. Now 3, its cube is 27, and S cube into S, it will be S4. Put the value of S, which is 10 to the power minus 3. Ultimately it will be 27, 10 to the power minus 12. But we have to compare with the options. But in options 10 to the power minus 12, it is like this. It is not matching, right? So we will arrange it in this way so that we can match it with the options. So we are using only 10 to the power minus 1. So now it will be 10 to the power minus 11, and it is matching with the first option. Okay. So in this way, we can calculate Ksp value, solubility product. In the next problem, we will calculate degree of dissociation, that is alpha. Molarity is given and the compound is acetic acid, weak electrolyte. That is why the question of degree of dissociation, because if it is NaCl or KCl strong electrolyte, there is no question of degree of dissociation. Okay. Conductivity, that is given 8 into 10 to the minus 5 Siemens per centimeter. So see, just from unit you can understand this is kappa. So sometimes it is mentioned as conductivity, sometimes it is mentioned as specific conductance or specific conductivity. All are actually same. And some more information given, lambda naught of H plus, that means infinite dilution values. These are all infinite dilution values. Okay. And it is per mole, that means it is molar conductance. So lambda naught of acetic acid, this will be equal to lambda naught of H plus, lambda naught of acetate ion. These two values are given, 349.6, 40.9, 390.5 S centimeter square per mole. Okay, so this is the value of lambda naught HOAC, and here from the value of kappa we can find out what is the molar conductance at a specific concentration, which is 0.0024, because we have to calculate alpha, and alpha means what? Lambda m of, that is at any concentration C, divided by lambda m at infinite, that is not, or you can use the infinite sign. So this we have calculated 390.5, but we also need this one. So how to find it? From kappa, by using this equation. Lambda m is 1000 kappa by molarity. Kappa is, be careful about the units, it is in centimeter inverse, so no problem, because this is also in centimeter inverse. 10 to the power minus 5 multiplied by 1000, molarity is 0.0024. Okay, so this will be, so put it here, 33.33 divided by 390.5. Okay, So see, this value is so low compared to this one because this is at infinite, so obviously it will be low, and this is equal to 0.085. So if you take the percentage, it will be 8.5%. Okay, so degree of dissociation, it is 0.085. This is the final answer. And if it is asking what is the percentage of degree of dissociation, then you have to multiply it with 100. So 8.5% is that degree of dissociation. You can understand how low it is. Out of 100 molecules, only 8.5 molecules of acetic acid will be dissociated when it is having this concentration. But when it is at infinite dilution, this has so high value.